Hello everyone, hope you guys are doing well and safe. Today we have a beautiful problem from the MIT entrance exam. So for sure everybody knows that MIT, Massachusetts Institute of Technology, I can say it's one of the best, of course, universities in the world in science and specifically in the mathematics. So this is a calculus problem, limit problem. It's pretty easy but beautiful problem. We are going to use a trick to solve this problem easily. So let's do this. What does it say? It says that we'll find the limit of x factorial divided by x to the power of x when x goes to infinity. Okay? So, of course, when we talk about the factorial, means x is gonna be a positive integer number, right? And for sure, everybody knows that. For example, n factorial is n times n minus 1 times n minus 2 all the way times 1. Okay, this is called the factorial. How to solve this? Okay, so when x goes to infinity, both numerator and denominator are getting bigger and bigger, okay? Um, but the thing is, we don't know which one is growing faster, okay? So can we use a L'Hopital rule that in one of the videos I introduced that? No, because how to take a L'Hopital, how to take a differential from x factorial, right? So unfortunately here it doesn't work, but we are gonna use a beautiful technique. It's called the squeeze theorem or sandwich theorem to solve this type of problems, okay? So when x goes to infinity, of course, we come up with infinity divided by infinity, which is unknown, undefined, right? How to simplify that to come up with something, a defined value? So the trick is I'm gonna introduce that here. So the squeeze theorem or the sandwich theorem. It says that can we place x factorial x to the power of x between two numbers? Let's try that. So we know that x factorial is gonna be similar to the n factorial that I introduced, that x factorial is x times x minus 1 times x minus 2 all the way times 1. Okay, so since these are positive integer, for sure, how many terms here? We have x minus 1, x minus 2 all the way times 2 times 1. Okay, 1 times anything doesn't change the result, okay? So that means in total here we have x minus 1 terms, okay, significant terms, okay? This guy doesn't change anything if you multiply by 1 or not. So that means I'm gonna say x times x minus 1 times x minus 2, etc. For sure, x minus 1 is less than x. X is less equal to x. X minus 2 is less than x. All the way to 2 is less than x in general form. Okay, note that x is general x. So that means from here, I can conclude that this x factorial, which is multiplication of x times x minus 1 times x minus 2 times all the way to 2 times 1, is gonna be, how many terms here is x minus 1 terms, okay? So that means x factorial is less equal to x to the power of, if you multiply x times x times x times all the way to x. How many times? X minus 1 times. To the power of x minus 1. This is interesting. Why? And of course, it's going to be greater than 1 as well, right? Because this is the minimum value of the factorial. So let me write it down again here. So x factorial greater equal to 1 less equal to x to the power of x minus 1. Now if I divide all three parts by x to the power of x, what I have here, the middle term is exactly what we are looking for the limit when x goes to infinity. Cool. So that means the limit of this one for sure is gonna be somewhere between the limit of 1 divided by x to the power of x when x goes to infinity and x to the power of x minus 1 divided by x to the power of x. So this guy is nothing just 1 divided by x. Okay. Now, what is the limit of this guy here when x goes to infinity? Okay, for sure it's gonna be 0. Okay, and what is the limit of this guy when the limit of 1 divided by x goes to infinity? This is gonna be, of course, 0. 1 divided by infinity, bigger is approaching to 0. Okay, now based on the squeeze theorem or sandwich theorem, so the limit of this guy in the middle is gonna be nothing just 0. When x goes to infinity, this limit is gonna be 0. Okay? Okay, cool. Thank you. Please subscribe the channel and share with your friend. Thanks so much.